Hi, NA Physics, it's Mr. Neff. Today I want to talk about dynamics of uniform circular motion. Before I do you know where monkeys cook their burgers? I'll tell you about that at the end of the video. Now, if I get out of your way, you're going to get to see my toy plane that's flying around. What I'd like you to do is get out a timing device. I'd like you to get the period of that motion, that is the time to go around once. Now, I would recommend not doing it by timing one cycle, but timing many and then dividing. I'm going to give you enough time now to do that. Okay, that should be enough. Now, we've done an activity something like this before. Now, what I did is I took 10 cycles of that plane and I timed it, and you can see from my phone here that I have a time of 14.65. Now, I only think 2 of those digits are significant, even though it looks like a 4 significant digit number. I know that this 0.65 is not really my uncertainty range. So what I'm going to say here is I have 14.65, 2 significant digits, seconds divided by 10 cycles. And that's going to mean that that was 1.465, again, 2 significant figures, seconds per cycle. So that's my period. Okay, now, off camera, I measured the radius, and the radius of that circle is 70 centimeters, 2 significant figures as well. And then I put the plane on the scale, and I got 135 grams for its mass. So now what I would like you to do is stop the video and use those numbers to do 3 things for me. Calculate the linear velocity, the meters per second, calculate the acceleration, and show me a free body diagram for the plane. Okay, stop the video and go ahead and get that started. All right, so I hope you have those numbers. For my velocity, I did, and this is the instantaneous tangential velocity, by the way. I did a distance divided by a time, 2 pi r divided by the period. Some of you may have thought that it's coming back to the same spot, and so an average velocity for the one complete period or 2 periods or 3 periods would have been 0, but I'm looking at an instantaneous velocity, and so I'm going to do that distance over time. Ironically, I got right around 3 meters per second. Be careful that you put a 0.7 in for the radius and the time that we calculated before. Now, to do the acceleration, we know that this is uniform circular motion, so we're not speeding up or slowing down, but we are changing direction. And when you're changing direction, at centripetal acceleration, velocity squared divided by radius, I took that 3, squared it, divided by 0.7, and I got 12.876. 2 of those digits are significant. 2 of those digits are significant. Now we're going to do a free body diagram, and so a little grid helps here. I'm thinking of the plane at that instant when it was pointed right at us. So there was, and you would have saw that at one moment in the frame. If I draw that, I think of the plane. I have the plane there, but I'm really just thinking of this dot as the plane. There's going to be a force of gravity. And when you multiply m and g together here, remember it was 135 grams or 0.135 kilograms. You're going to get 1.323. 2 of those are significant because of the 9.8 newtons. Okay. Then you also have a tension. Now, the tension is from the string, and it's going to do 2 things. It's going to balance out the force of gravity, exactly. So it's going to have a y component that is going to look like that, the same size, force tension y. And it's going to have an x component that is going to accelerate you towards the center. And I don't really know how big to draw that right now, so I'll draw this, but we may have to come back later and change the size of that. And so these are the 2 components. The one tension is this diagonal one that goes like that. And so maybe some would say that we should just draw this, which is fine, but I'm going to go ahead and leave those other ones on here because I think that's a pretty good looking picture. Now, it is that force that's pointing towards the center. The center of the circle is over here on the left. That force that's pointing towards the center, that is going to be that force of tension X component, is going to be the thing that's causing this to go around in a circle, causing that centripetal acceleration. And that's where the new part comes in. We're going to call that a centripetal force. It's a net force that's causing circular motion. The centripetal force is it's a good name and a bad name. Centripetal, of course, means going towards the center, which is a great name. But when you think of centripetal force, and even the symbol FC, it makes you think that it's a particular force. No, the centripetal force is a special case of the net force. And so where the net force was always a combination of forces and other forces had to come in and be the net force, well, the same thing with the centripetal force. So the centripetal force is a net force that causes you to go towards the center. Now, if the centripetal force is the net force, well, then calculating it is actually really simple after you've been through Newton's laws. It's just the mass times the acceleration. Thing is, when it's a centripetal force, you're not going to use change in velocity over time. You're going to use v squared over r for the acceleration. So we like to put a little c subscript down here to indicate that that's a centripetal acceleration. So go ahead and use your machine to verify what I'm doing here, but I'm going to take the mass of the plane, 0.135 kilograms, and multiply by the acceleration. Remember, that was 12.876. You can go back in the video if you want to see that calculation. I know you had that from before. And I ended up getting a centripetal force of 1.73826 newtons. And please, don't lose track of what that is. That is the amount of force that we know we have because of what's happening to the plane, the mass and the acceleration we're seeing. And so that is how large this centripetal force is right here. What is the centripetal force in this particular case? A component of tension. You'll see a lot of examples where it's gravity or it's normal force or it's friction or it's all kinds of different things. So now I ask, what is the tension? Stop the video and calculate the tension real quick, please. All right, so the tension is equal to the force of tension X plus the force of tension Y. Now, no, I'm not telling you to just simply add those two components together because, and see, I'm not telling you that because I have the vector symbol above. I'm telling you to add them together head to tail. So just like I have in my free body diagram at the top of the screen, I'm going to use a Pythagorean theorem and get a hypotenuse value. So that's going to be 2.2 newtons. Now I ask for the net force. Stop the video and calculate that for a second. Okay, and we're back. The net force is the mass times the acceleration, whatever acceleration is times whatever the mass is. And so we've done that already, haven't we? We took the mass already and we took the acceleration already and we have the 1.7. You could also think of it as the force of tension Y and the force of gravity are canceling each other out. And so what we have left is the force of tension X. So to summarize that, the centripetal force is a special version of the net force. It's when the net force is always pointing at a particular spot, the center of the circle, and it's causing circular motion. So centripetal force is going to be a job that some other force is going to have to come in and do, or maybe a combination of forces, just like net force is. So moving in a circle is a forced thing. It's an accelerated thing. We know that. We saw that in our kinematics work. Now we see that if there is acceleration, there must be net force. In a circle's case, that's going to point towards the center. You hear that, but do you believe that? Let's see if you do. I have 3 video clips here. The first video clip is going to be a pair of students, and one student is going to roll a bowling ball, and the other is going to use a croquet mallet, a big hammer, to make it go in a circle. How could that be done? Well, it's like this. There it goes. And see, what has to be done is the bowling ball wants to keep going in a straight line. You'll see that at the end, it will do that. So what he has to keep doing is keep correcting its path by hitting it towards the center. As soon as he stops hitting, see what happened? It stopped moving in a circle. Now along those lines, this is going to be a ball that's going to go around and around in this ring. And you can see this yellow piece over here is removable. Whenever the ball rolls around a couple times, then the student is going to remove that piece of the ring. And so the ball's going to roll around like my mouse is, and it's going to get to here. The ring piece is going to be removed, and then it's going to encounter this area that no longer has a ring. What's going to happen? Well, you just saw a clue of that, didn't you? In this case, you're going to have a centripetal normal force from the ring. And as soon as that centripetal normal force stopped, see what happened? The ball is no longer forced in a circle, and so it stops doing a circle, you see? So first time I had a centripetal applied force from the hammer, second time I had a centripetal normal force from the ring. And now the same group did a third video on roller skates. And so see what they do is one student has the roller skates on, and she just kind of leans into the center, but that wasn't very circular. And so now what they'll do is they will use a rope to pull her into the center. Now that's a good circle right there. Why? Why is that so good? Well, it is because, see, there's a force that's always into the center. In fact, that's the best circle you saw all day, aside from the one that was in the ring. Now here's something that's okay, more like the bowling ball in the first place. As she pushes into the center, but not as good as the string, because she can only push intermittently into the center, not all the time. So then to summarize, to make something move in a circle, what do you have to do? Stop for the video for a second, think about that for yourself, and then come on back. Okay, very good. So to make something move in a circle, of course, we're going to have to make it move in a circle. And so we're going to constantly push it towards the center. That is, accelerate it centripetally with a centripetal force. Now that word centripetal we've talked about before, which let's just rehash a little bit of that. Centripetal means moving toward the center. It comes from Latin. That literally translates as center seeking. And so that force is going to make the velocity change towards the center, or seek the center. So centripetal force, like I've been saying, is not like other named forces, but it's a net force. So some other force is going to have to come in and be the centripetal force. You might have a ball and a string, and here we have a centripetal tension force. You might have a car going around a curve, and we have a centripetal friction force. You might have a roller coaster, and actually here the centripetal force is going to be a combination. It's going to be the force of gravity minus the normal. See, the center of this roller coaster is down here, and so how big is the net force? Well, force of gravity minus normal. That probably reminds you of an elevator a little bit. You could be large scale. Here's the Earth and the Sun, and we have a centripetal force of gravity making the Earth orbit the Sun. And here we have a hammer thrower, and there you see a centripetal tension force. So some force has to come in and be the centripetal force. Now, caution. The centripetal force is easily calculated. It is net force, and so you can just take the second law and you can say the centripetal force is the mass times the centripetal acceleration. That looks new and exciting, and it is exciting, but it isn't really new. Careful, centripetal is not the same as centrifugal. I've talked about that before. Centrifugal means going away from the center. It's actually the complete opposite of centripetal, so be careful of that. And a lot of times in a case like this, people will think they see centrifugal forces. Sure, when you go around in a circle, a lot of times it seems that things will move centrifugally whenever there's not enough force to make them go in a circle. So these kids are moving centrifugally, finding the right radius for the speed. You can even find a picture like this online, and it looks really good, looks like a great free body diagram. But I disagree with it totally. The centrifugal force isn't really there. That's really just the inertia. And you can even see this car commercial. They're spinning the sand off of the car tires, and see the sand is moving centrifugally.